Assalamualaikum and good day everyone. So as for today, we are going to continue with our lesson, right, which is for the design of serviceability, for serviceability, right. So we will proceed to the cable zone limits, right. So we have already done with the manual diagram construction, right. So this is for the next one, whereas we are going to go for the cable zone limits. Right, so first we will go through the lesson outcomes, right. So at the end of this lesson, you should be able to determine the cable zone limit in a pre-stressed concrete beam, right. So basically we are going to use equations, and also we will be using the values of the pre-stressed force, that has been determined from the Magna diagram, in order to determine the cable zone limits. Okay, so for the design of tendon profiles, so once the pre-stress force value had been determined, which satisfies all the stress conditions and also the at the critical section, it is necessary to determine the eccentricity, which is the location at which this force must be provided. Right, so based on the Magna diagram, right, we have already determined the value of P naught, right? So we have already determined the range of P naught value, right? So from there, we are going to choose one value, and we are going to determine the eccentricity, not only at the critical section, but also throughout the length of the structure. Right, so if, for example, if we have a 12-meter beam, right, so therefore we are going to determine the location of our tendons at the um, end span, as well at the middle of the beam. Right, so at any section along the member, E is the unknown term in the four equations, which are equations 5 to 8. Right, so these are the equations that we have used previously, in order to check our value of the pre-stress values, with the stress limits. Right, so we can see here that we have this E value, which are actually the unknown value. Right, so we are going to rearrange this equation, in order to get the equations for eccentricity. So equations 5 to 8 yields two upper and two lower limits that must be simultaneously satisfied. Right, so this requirement must be met at all sections throughout the member. So it will reflect both variations of moments, pre-stress forces, and also the section properties along the member. Right, so from equations 5 to 8, right, so we can see here that we have already rearranged the equations to have this E value or the eccentricity on our left. Right, so this will be our unknown. Right, so and here in the equation we have this bracket, whereas we can see that we have ZT over A, minus with the stress limits, multiply with the section moduli, divided by the P naught value, which is the pre-stress force. So we are going to do this for both transfer and also at service. So these equations can be evaluated at any section, right? So meaning to say, that we are going to determine the values, for both at the end span and also for the mid span. So it is to determine the range of eccentricities within which the resultant force P naught must lie. So M maximum and also M minimum are related to the section considered. Right, so we can see here that we have M minimum, for transfer, and also we have M maximum for the for at service. Right, so for the tendon profiles, right, so for members of constant cross section, whereas from the beginning to the end of our beam, right, we have a constant cross section. So if minor changes in the pre-stress force along the length are neglected, right, so therefore the terms in the bracket, which is in this bracket of equations 21 to 24 are considered as constant. Right, so it is constant, because it is not actually depending on the value of the bending moment. Right, so therefore the zone within which the centroid must lie is governed by the shape of the bending moment envelopes. Right, so we can see one example here, on this figure. Right, so we have a simply supported beam, and also we have the centroid in the middle. Right, so here, we'll be able to draw the curve. Right, so we have this first curve, which is based on this equation. Right, so we can see that we have ZT, over A, minus with F prime minimum ZT over P naught. right? So we only have this equation, okay, because at the ends here we do not have any values of moments, right? But towards the midspan, okay, of our beam, we are going to have additional value of the bending moment, right? So we have M minimum here, right? So this value, okay, of this equation in the bracket will be add up to this value, okay, which is considering the bending moment, right? So we have the first curve here, right? Then we have another curve here, okay, which is the curve for another equation. Okay, so we have negative ZB divided by A plus with F minimum ZB divided by KP naught. Right, then this is for the end span, right, which is for these 2 points here. Okay, then plus with the moment maximum, right? So when we plus up with this moment maximum, so therefore we end up with a new point here, right? So here, okay, we are going to have this curve, right? Okay, so these are the two equations, okay, that give us the curve or the zone, okay, that is for our section. Right, so in case of uniform loading, the bending moment envelopes are parabolic. So the usual practice is to provide parabolic tendon profiles if the straight tendon profiles does not fit within the zone. Right, so usually for pre-stressing tendons, okay, usually we are going to provide parabolic tendon profiles. Right, so why is this? Okay, because usually we are going to have the bending moment that is clearly it is radially parabolic bending moment. So at the critical section, okay, the zone is generally narrow, okay, and reduces to zero if the value of pre-stress force is taken as the minimum value from the Magnell diagram, right? So if we are taking the minimum value, okay, from the Magnell diagram, okay, as what we have determined previously, maximum and also minimum. So if we are referring to the minimum value, okay, usually, okay, at the critical section, which is at the middle section of our beam, okay, the value here will be equal to 0, right? Okay, whereas these two curves will touch, right? So at sections that is away from the critical section, the zone becomes increasingly greater than the minimum required, right? So we can see here, okay, if we refer back to this slide, right? So we can see here at the critical section, okay, which is the mid section, the area is very small or very narrow, okay, but towards the end of the beam, okay, we are going to have the value, the zone, okay, that is much larger. Okay, so now we go to the example. So we have example 5 for cable zone calculation. So determine the cable zone limits at midspan and the ends of the member designed in the previous examples. Okay, for a constant initial pre-stress force of 700 kilonewton. Right, so we are already given this value of 700 kilonewton, which is selected based on the range that we have determined from the Magnell diagram construction. Right, so we are going to use the similar design data, okay, that we have used previously. Right, so we have the stress limits, okay, then we also have the pre-stress loss, section moduli, the A value, right, then we also have moment minimum and moment maximum. Right, so for the end span, we are going to substitute, okay, the values into the equations. Right, so we can see here, okay, that since at the end span the value of moment is equal to 0, so therefore in the equation here, okay, we are going to substitute here, okay, and the value here will be cancelled out. Right, then we have equation 21, 22, 23 and also 24, right? So these are the values that is given in the range of inequalities, right? So we have E less or equals to 64.12, E less or equals to 21.14, and also negative 116.57 and also negative 58.29. Right, so based on those values, okay, we will be able to draw, okay, this range of eccentricity. Right, so this range of eccentricity, okay, which can be seen here. Right, so based on the equations, okay, we can actually draw, okay, the inequality requirements, okay, for each equations. Right, so therefore from there, okay, we will be able to determine this boundary. Right, okay, so therefore the E value or the eccentricity must lie within this range. So this is for the end span. Okay, so next we are going to repeat the same method or the same step, okay, for the midspan. So we are going to use the similar values, okay, similar equations, sorry, right, which are equations 21 until 24, right? Only that now you can see the difference is that we are going to have the values of the bending moment, right? So we have moment minimum, okay, for the values of E at transfer, okay, and also we have moment maximum, okay, which is for the E value at a service, right? Okay, so we are going to end up, okay, with these values of inequalities, okay, and based on that, okay, we can draw the range of eccentricity for midspan, right? So similarly for the end span, so we can draw this as well, right? So we have this, okay, for all four equations, and we can determine the range of eccentricity, okay, for this part, right? So we have here, it is between 47.78 to 60.43. Right, so this E must lie within the range of 47.8 to 60.43. So provided that the tendons can be arranged so that their resultant force lies within the calculated limits, right? So therefore that would be considered as an acceptable design, right? Okay, so we have to follow this range, okay, that has already been given by the equations. Okay, right. So this range of eccentricity can also be determined using the Magnell diagram, right? So just now, from the question, okay, we are given the value of P naught, okay, which has been determined as 700 kilonewton, right? So if we are not using the equation, okay, the range of eccentricity for the midspan can also be determined based on the Magnell diagram, right? So as you can see here, if we plot the value, right, so we are given this 700 kilonewton, okay, as our initial pre-stress value. So what we have to do is that we have to recalculate back, right, because if we are to include the value, okay, into this Magnell diagram, so therefore the P naught value will be this, okay, because we have the vertical axis as 10 to the power of 6 over P naught, right? So 10 to the power of 6 over P naught, okay, is equals to 1429, which corresponds to this P naught, which is equals to 700 kilonewton, right? So we have this point. So from this point, what we are going to do is that we are going to draw a line, right? So a line, okay, from this P naught value, okay, to coincide, okay, with the permissible zone, right? So you can see here, okay, this is the permissible zone, okay, so this is our line, okay, which is from the initial value, right, that we have already decided, okay, based on this range of pre-stress force, right? Okay, then based on that, okay, we are going to go for these points, okay, where we have the intersection points, and here is actually the value of the eccentricity, right? Okay, so we can see here that we have 47 at this first point, then we have 60 at the second point, right? So even though the value of this eccentricity is not as accurate as if we are using the equations, okay, but however, okay, we can actually estimate, okay, the eccentricity value of where our pre-stress force or pre-stress tendon must lie, right? So we can see here that we have this 47, okay, and also 60. So this is the range of eccentricity for the midspan, right? Okay, so these are the two methods, right? So we can either use the equations or we can also use the Magnell diagram, right? And after we have already determined all the range of eccentricities, right? So using the values, right? So we can actually plot, okay, the tendon profile, right? So which will show us, okay, the cable zone limits, right? So you can see here, this is one curve, okay, that we can draw based on equation 21, right? So we have the point here, okay, that is for end span. So this is for the 2 points. Okay, then for the center point, okay, or the midspan, okay, we are going to plot based on the value for the midspan, okay, that has been calculated for the midspan, right? Then similarly, okay, this is for equation 22. Okay, then we can also plot for equation 24 and also equation 23, right? So we can see here, based on all these equations, okay, we are going to be able to determine the cable zone limit, right? Okay, where the location of the pre-stress force should lie, right? So here, okay, we have these two lines, okay, that corresponds to all these four equations, right? So this is the cable zone limit, okay, that we can the cable zone, okay, that we are able to actually determine, okay, and also put our pre-stress tendons, right? So this is the cable zone, okay, and you can see here, okay, we can measure, okay, as what I've shown you just now in the previous figure, right? So we have this M max over Kp naught, okay, which is 106.07, okay, and also we have another value of M minimum, okay, over P naught, which is equals to 31.29, right? So these are the values, okay, involving the cable zone, right? And this is the cable zone limit, right, which is in orange, right? So this is the cable zone, okay, that we are going to provide our pre-stress force into, right? So this is the tendon profile, right? So after we have already calculated the E values, okay, for the end span and also for the mid span, right? So this will be the uh, kind of uh, result, okay, what we are going to get, right? So from here, okay, we will be able to actually determine the location, okay, of our pre-stressing tendon, right? So the width of cable zone, so from the Magnell diagram, for any chosen value of pre-stress force, there is an eccentricity range that the resultant tendon force must lie. So as the force approaches a value that corresponds to the top and bottom limits of the Magnell diagram, okay, the width of the available zone diminishes. Okay, so the giving zero width of cable zone, right? So this is um, within the critical section, okay, which is usually in the mid of span, right? Okay, so it says that if it is going for the top and bottom limits of the Magnell diagram, right, so therefore the width of the cable zone will be much narrower, and sometimes the value will be equal to 0. So practically, a pre-stress force will be chosen in between the upper and lower limits of permissible pre-stress force, right? So once we have determined the maximum and also minimum value from the Magnell diagram, so usually we are going to go for the value that is in between those minimum and maximum. So instead of just selecting the minimum and maximum values, right? So this is actually to ensure a reasonable width of the cable zone, right? So if we refer back to this figure, right, so we actually wanted to have this reasonable width, okay, of the cable zone, which is usually at the middle here, right? So that is why we need to choose a correct value, okay, that is reasonable in between those maximum and minimum values, right? Okay, then the last one, okay, the pressurizing cables, okay, must also satisfy, okay, the cover requirements. So when we talk about cover requirements, okay, it means that we are satisfying the requirements for the exposure conditions, right? So it is actually similar to the previous concept, okay, that we are using in the reinforced concrete design. Right, then we also have minimum spacing between tendons, right? So usually when we talk about minimum spacing between reinforcements or between tendons, okay, usually we are going to fulfill, okay, the requirements in order to make sure that we have a section that is fully compacted, right? So to ensure full compaction, okay, of our structure, okay, therefore we need to have this spacing, okay, between the tendons. Then also we have to consider the available size of tendons, right, in the market. Right, so a number of alternative tendon combinations and configurations shall be tried, right, to ensure all requirements are met. Right, and the advantage of using the Magnell diagram, okay, is that the range of alternatives can be quickly considered. Right, so if we can uh, directly determine, okay, based on the pre-stress force value, so we can actually adjust, okay, based the eccentricity value, okay, based on the Magnell diagram. So instead of doing the calculations, okay, we can also do the determination of the E value, okay, based on the Magnell diagram, especially for the mid span, okay, whereas we are required to determine how big, okay, is the width of cable zone that we are going to use. Right, so I suppose that would be the end, okay, of our lecture as for today, right, okay, which is with regards to the cable zone limits, right. So if you have any questions, right, then feel free to contact me through WhatsApp, okay, or you can also go up and contact me through Teams, right. So you can also try to answer the questions from the past year questions, okay, on this tendon profile. Okay, so with that, thank you. Assalamualaikum.